All right, we are going to start chapter 5 for pre-calc. It's called analytic trigonometry, so we are going to use all of the information we learned in chapter 4 in terms of the graphing and the unit circle to analyze and solve equations involving trig. An overview of our chapter. It says in this chapter you will learn that trigonometry, with its many connections to triangles and circles, enables us to extend the problem, solving tools of geometry significantly. We hope in the process to give you an appreciation for the rich and intricate tapestry of interlocking patterns that can be woven from the 6 basic trig functions. So we are going to split this into 2 parts. We will test on the first 3 objectives here, looking at the fundamental identities, proving trig identities, and looking at the sum and difference identities. And then in the second half, we'll deal with multiple angle identities and law of sines and cosines. So for our first section here, our objectives are to be able to identify and work with the trig identities. We're going to learn about the basic ones, which we've already introduced in chapter 4, the Pythagorean identities, cofunction identities, and odd and even identities. We're going to simplify trig expressions using those identities, and we're going to solve trig equations using those identities. All right, so this is just a quick review from the last chapter. It says, without having a unit circle in front of you, give the simplified, exact, rationalized answer. So I want you to think of our 3 basic angles. We've got pi over 6, we have pi over 4, and we have pi over 3. And think about what the ordered pair would be for each of those. All right, so our pi over 4s are the easy ones. That's the root 2 over 2s. All right, the pi over 3s and pi over 6s, we have to remember which one's which. In pi over 6 angles, our sine is 1/2, which is our y-coordinate. That makes our x-coordinate our root 3 over 2. And for the pi over 3s, it's just the reverse. Our cosine is 1/2, and our sine is root 3 over 2. So just remember that cosine is your x-coordinate and sine is your y-coordinate. So if I want the sine of 2 pi, I have to think of where am I at when I go to 2 pi, and that would be all the way around and back to where we were at 0. And the sine of that, this has the ordered pair 1, 0, so my sine would be 0. For the cosine of 3 pi over 2, 3 pi over 2 puts us here at either negative 90 degrees or positive 270 degrees. And the cosine would be our x-coordinate, which in this case would be 0. For the tangent of pi over 6, remember tangent is y over x, or sine over cosine. So if we go to our pi over 6, we're looking at 1/2, the sine value, divided by the cosine value. Those 2's are going to drop out, which gives us 1 over root 3, which would be root 3 over 3 if we rationalized it. For 7 pi over 4, think about where we would be at. We need to go 7/4, which puts us halfway through this 4th quadrant. Pi over 4s are the root 2 over 2 combinations, but in that quadrant our sine is negative, our cosine is positive. So we need, for cotangent, x over y, so we have root 2 over 2 divided by negative root 2 over 2, which gives us negative 1. And for 5 pi over 6, again, if you picture where we are, 5 pi over 6 would be right in here. So we are looking at our pi over 6 reference angle. Secant is the reciprocal of cosine. So we need the reciprocal of our root 3 over 2. But in this quadrant, cosine is negative. So we need 1 over negative root 3 over 2, which would be negative 2 over root 3, and rationalized would be negative 2 root 3 over 3. So what I'd like you to do is pause the video and try the last 5 here, and then turn it back on and check your answers. Okay, for cosecant of 5 pi over 3, 5/3 pi, half our circle would be 3/3, then we need to go another 2/3, which puts us here. Our reference angle would be a pi over 3, which has coordinates 1/2 root 3 over 2. And in this quadrant, x is positive, y is negative. We need the cosecant, which is the reciprocal of our sine value. So we need 1 over negative root 3 over 2. Reversing or taking the reciprocal of that would be negative 2 over root 3, and rationalized would be negative 2 root 3 over 3. All right, for cotangent of 4/3 pi. 4/3 would put us 1/3 into our third quadrant here. All right, so again, we're looking at a pi over 3 reference angle. Same angle we have here, except both of them are negative. So negative 1/2, negative root 3 over 2. And we need the cotangent, which would be x over y. So we have negative 1/2 over negative root 3 over 2. The 2's drop out. The two negatives would cancel out. We get 1 over root 3, which would be root 3 over 3 when it's rationalized. Secant of pi. We're over here, negative 1, 0. Secant is the reciprocal of cosine. The reciprocal of negative 1 is negative 1. For 7 pi over 6, we are 1/6 into this quadrant. All right, so we're looking at a pi over 6 reference angle, and we need the sine of it. In this quadrant, sine is negative, so we know we're going to have a negative answer, and our sine value is 1/2, so negative 1/2. And cosine of 2 pi over 3, we're over here. All right, so we have a pi over 3 reference angle. Using our pi over 3's, we need cosine, which is our x coordinate. So our cosine in that quadrant is negative, so negative 1/2. All right, so the first thing, it says the symbol equal means several different things. It can be representing the equality of numbers, like we know 1 + 1 = 2, which is a true statement for all numbers. We know that equal signs can be used to show equivalent expressions, like 2 times the quantity x minus 3 is 2x minus 6, is basically just saying that the two sides are equal. We can use equality symbols in an open sentence, like x squared plus 3 = 7, which is sometimes true. It just depends on if your x is a solution to that or not. And then the equal signs can be used in an identity, and we're going to be looking at a lot of trig identities in this chapter. So one of them says cosine of t squared plus sine of t squared = 1. It's based on our Pythagorean theorem. Equations that equate two expressions that are true for all values in the domain of both expressions. So this idea of our domain of validity says values of the variable for which both sides of the identity equation are defined. That means I need to look at both sides of my identity, or both quantities, for example here. All right, I need values for t which are defined. Okay, that's what that's meaning. So our first trig identities for the chapter are ones that we've actually already talked about. Cosecant we've defined as the reciprocal of sine. Secant is defined as the reciprocal of cosine, and cotangent is the reciprocal of tangent. So that top row is dealing with the reciprocal ones. The second row here is just another way of saying it. So if cosecant is the reciprocal of sine, then sine is the reciprocal of the cosecant. Okay, and that works for all three different trig functions, sine, cosine, and tangent. The quotient identities are the combinations, and we've talked about those again in chapter 4, where tangent is defined to be sine of theta over cosine of theta, or y over x, and cotangent is the reciprocal of that, so cosine over sine, or x over y. All right, so the first question says if theta is 0, so picture being here right at 0, all right, think about our typical ordered pair that we use, the point 1, 0. It says theta being 0 is in the domain of validity of exactly 3 of our basic identities. So which 3 can we actually solve or use when we are at 0 degrees? So if you think about it, because of this 0 here, any time that that is in the denominator, it causes problems. It's not defined. We can't divide by 0. So let's look at our trig identities and find anywhere that y coordinate would be in the denominator position. So for example, this first one here, we are taking 1 over the sine of theta, but the sine of theta is 0. So that would not work. Okay. For secant, we're taking 1 over the cosine, but cosine's 1, so that looks like that would be fine. Secant of theta is 1 over cosine theta, so that is one of the ones that work. For cotangent, we're taking 1 over tangent, and tangent is y over x, so this would be 1 over 0 over 1, but 0 over 1 is 0, and this simplifies to be 1 over 0, which we cannot do. Okay. Below, we've got the sine being 1 over the secant. Well, sine is 0, so that would be saying 0 equals 1 over cosecant, which is the reciprocal of sine, or 1 over 0. And that is undefined. We can't divide by 0. So our sine one doesn't work. Since secant worked, let's look and see if cosine works. We are taking cosine of theta, which is 1. We are taking 1 over the reciprocal of the cosine, but the reciprocal of cosine of 0 is 1, and that is defined. So cosine of theta equals 1 over secant theta. It works for those. The last one here, tangent of theta is 1 over cotangent. We said here cotangent was not defined, so that doesn't work. But what about this one? Looking at it this way, can we take sine over cosine? And we can. In this case, sine is 0, so we'd have 0 over 1, and that is defined. All right, so we can say that the tangent is also one of the identities where it is in the domain of validity. All right, the second one says, for exactly 2 of the basic identities, one side of the equation is defined at 0 and the other side is not. So take a second and pause the video and then see if you can pick out 2 where one side seems to work but the other side does not. All right, so the first one where it does not work, we have the sine of theta being 1 over cosecant of theta. Sine is fine. The left side of that would be okay because the sine is 0 and that is defined. But on the other side where we have 1 over cosecant, we are taking the reciprocal of sine. So the reciprocal of 0 is 1 over 0, and that's where it doesn't work. Okay? The second one where it doesn't work on one of the sides was this one. Okay, the tangent is y over x, so this becomes 0 over 1, which is fine. That side is okay. But on the other side, we would be saying that we'd have 1 over x over y, and it's not valid right there. Okay, so those are the 2 where it works on one side but not the other. All right, the third question says, for exactly 3 of the basic identities, both sides of the equation are undefined at 0. And which 3 would that be? So if we think about the ones where we've already used, let's go back here. All right, we have said that it works for this one. We said it works for cosine, this one. And we said that it works for the tangent being sine over cosine, that one. We said it works on one side but not the other for the sine, this one, and for the tangent being 1 over cotangent. All right, so of the ones that we have remaining, they're basically saying it doesn't work on either side. All right, so the ones we have left over, cosecant of theta is 1 over sine. Okay, sine of theta is 0, so that doesn't work. We can't have 0 in the denominator. And the cosecant is the reciprocal of sine. All right, so it's not going to work there as well. The other one that was left, cotangent of theta is 1 over tangent. And the third one, cotangent of theta is cosine over sine. So again, we're just making sure that both sides of the identity are defined. All right, if they're not, we don't consider it in the domain of validity. All right, a couple new identities. The Pythagorean identities are based on our Pythagorean theorem, that's why they're named that. And the first one we've talked about a fair amount of times in chapter 4, that cosine squared plus sine squared equals 1. It's based on our x squared plus y squared equal r squared, and r is always 1 in a unit circle. The other two identities can be found by taking that first one and dividing either by cosine squared or by sine squared. So look what happens if we take our original cosine squared plus sine squared equals 1 and we divide everything by cosine squared. Okay, so cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is the same as saying sine over cosine quantity squared, and that's just tangent. So we end up with tangent squared here. And then on this last piece, I'll move the 1 over here so we can see it better. We have 1 over cosine squared, and the reciprocal of cosine squared is secant squared. Okay, and so that is our second Pythagorean identity, which basically means if we memorize the first one, we can generate the others. Okay, if we divided by the sine squared instead, all right, so we have cosine of t squared divided by sine of t squared, that is cotangent squared. If we take sine squared divided by sine squared, we get 1. And if we take 1 over sine squared, that is the same as cosecant squared. Okay, so again, of all of those three Pythagorean identities, if we memorize the first one, we can generate the other two simply by looking at what happens when we divide either by a sine squared or a cosine squared. All right, so example 1, it says find the sine of theta and cosine of theta if we're told the tangent is 5 and that the cosine is positive. So let's think about that. In what quadrant is cosine positive, which means our x-coordinates are positive, which means we could be in 1 or 4. And if you think about the signs of your coordinates, in quadrant 1, both x and y are positives. In quadrant 2, x is positive, y is negative, which would mean that our tangent would be negative in that quadrant. And since they're telling us the tangent is 5, that means we have to be in quadrant 1 somewhere. Okay? So let's go through. We have a tangent value, so we can use our Pythagorean identity that deals with tangent. So our identity is 1 plus the tangent squared of theta equals the secant squared of theta. And we know that the tangent is 5, so we have 1 plus 5 squared equals secant squared. And if we combine this, we get 26. If we square root, we would get plus or minus the square root of 26 equals secant of our angle. And then we need to do its reciprocal to get cosine. So we need the reciprocal of this. And then we have to say, but cosine it said had to be positive. So I'm going to ignore that negative and say we just have 1 over the square root of 26 as the cosine of our angle. Okay. Now, to find the sine, there's a couple options. We can go back and use one of our other trig identities. We could go up here and pick cosine squared plus sine squared equals 1. Now that we know what sine is, we could plug it in right there and solve for cosine. We also could take our definition of tangent, which was 5, and tangent is sine over cosine. So if we solve this for sine, we have the tangent times the cosine, giving us our sine. And tangent was 5. Cosine was 1 over the square root of 26. So our sine value would be 5 over the square root of 26. Okay? All right, we have quite a few more identities we're going to look at. They're fairly basic ones, and these first ones are ones that we have seen in Chapter 4 again. Just defining sine and cosine in terms of our x, y's, and r's. We said sine was y over r, cosine is x over r, tangent y over x. And then the other three are just the reciprocals of those. Now notice in this chart they are referring to angle A, using that as our theta or our angle that we're referencing, and they also give us the same ones in terms of angle B. Okay, so if we are using this as our angle, then our sine is x over r, our cosine would be y over r, and our tangent would be x over y. So it really depends on the angle that you're referencing in terms of those sides, which is why when we set up our angles, we always drew our triangle and had that angle theta be in the standard position, so our x's and y's made sense in terms of our ordered pairs. Okay? The next chart deals with the cofunction identities. We had one exploration in Chapter 4 where we looked at this and said complementary angles. All right, so think about if we have an angle theta and we take 90 or pi over 2 minus theta, those are complementary angles. Okay, so we're saying that the sine of the complement is the same as the cosine of the original one. The cosine of the complement is the same as the sine of the original one. And that works for tangents and cotangents, secants and cosecants as well. And the last identities for today are the even and odd identities. When we think about our reference angle, okay, if this is theta, we'll draw in a negative theta. Okay, we have ordered pairs. If we call this our point xy, okay, in the next quadrant down, if we reflect that over, our x stays the same, but our y is negative. Okay, so when we look at the sine of the negative angle is the opposite value of the sine of the original. So we went from having a positive y here to having a negative y. For cosine, the cosine of the negative angle and the cosine of the original angle are the same. And for tangent, because it's sine over cosine, or y over x, if we take the original angle, y over x would be positive. If we take the negative angle, we end up with a negative value. So again, the tangent of the negative angle is the opposite of the tangent of the positive angle. So if you think back to how we defined even and odd functions, we said even functions are ones where the value is the same. Whether you put a negative angle in here or you put a positive angle in, you should get the same answers out. So this would be an even function. All right, odd functions are the ones where we get the opposites out. So this set would be odd, and so would this. All right, example 2. It says if the cosine of theta is 0.34, find the sine of theta minus pi over 2. Now be careful here, because theta minus pi over 2 is not the same as pi over 2 minus theta. Those are opposites. Okay, so let's start out saying the sine of theta minus pi over 2. If we flipped that around, we could say that is the sine of negative pi over 2 plus theta. And if we factor a negative sign out of that, we get pi over 2 minus theta, which is our complement. Okay? So we're basically saying, let's factor that negative out. All right, let's pull that out. So the sign of the complement is the opposite. So we have negative sine pi over 2 minus theta. And if you look back up at our identities for cofunctions, the sign of the complement is the same as the cosine of our original. Okay, so this part right here, the sign of the complement is the same as the cosine of the original. But because we had to change the orientation of these two and get this negative pulled out, we are going to have it be the opposite. Okay, so that negative sign is brought down. And so if the cosine of the original angle is 0.34, then the sine of theta minus pi over 2 would be the opposite of that, negative 0.34. All right, the second part says using identities, simplify the expression to 1 or negative 1. All right, so we're starting out with the sine of x times the cosecant of negative x. Well, let's go back up here. The cosecant of negative x is the negative cosecant of x. Okay, and cosecant of x is the reciprocal of sine. And if you multiply the sine of x times negative 1 over the sine of x, your sine of x's are going to drop out, and this becomes negative 1. All right, example 3. It says to simplify by factoring and using our identities. Simplify the following trig expressions to a power of a single trig function. So when you first glance at them, notice that there's different trig functions involved. The first one has sines and cosines. We want to get this down to just a single type of trig function. So looking at our sine cubed plus sine x cosine squared of x, could we factor a sine of x out of all of that? All right, this is the idea that they said try factoring. If we take a sine of x out, we end up with the sine squared plus cosine squared left over. All right, and one of our Pythagorean identities is that sine squared plus cosine squared is 1. So this becomes the sine of x times 1, or just sine of x. So we have simplified it down to a single trig function. The second one, we have secant of x minus 1 times secant of x plus 1. Let's think of foiling that out, because if we look at it carefully, it looks like we have that idea of conjugates here. Secant minus 1 times secant plus 1 becomes secant squared. Insides and outsides would drop out, and we end up with secant squared minus 1. Going back to our Pythagorean identities, secant squared is defined to be 1 plus tangent squared. Okay, so this here turned into this, and then we have a 1 minus a 1. Those cancel, and it just becomes the tangent squared. Example C. We have 1 over cosine, which is really just secant. Okay, so this is secant theta minus 1. Looking at our second parenthesis, we have cosine squared. And let's look at that secant of negative theta. We don't want two different types of angles. If we have one being a positive theta, we want them all to be that way. So going back to our, let me scroll up here, flip back a couple pages. All right, to our even-odd identities, we have the secant of negative theta. If you look here, the secant of negative theta is the same as the secant of theta. So we can simplify this piece right here. That's the same as secant theta. And then 1 over cosecant of squared theta, the reciprocal 1 over cosecant is the same as sine, and it's squared, so we have plus sine squared theta. All right, now looking at that second set of parentheses, notice that we have a piece here. We have a cosine squared theta plus a sine squared theta, and our Pythagorean identity says that that's just a 1. So this becomes secant theta minus 1 in the first parenthesis, and we have 1 plus secant theta in our second one. Or we could write that as secant theta plus 1 so that we have that idea of conjugates again. Okay, and it basically turns into that second piece of that we just looked at. So we end up with that tangent squared again. All right, let's try to get one more example in here. It says simplify the expression secant plus 1 times secant minus 1, all of that divided by sine squared. Well, we've done this already twice here. Secant of x plus 1, secant of x minus 1 turns into secant squared of x minus 1. The whole thing is being divided by sine squared of x. All right, well, secant squared minus 1, our Pythagorean identity says that is tangent squared. And tangent squared is defined to be sine squared over cosine squared. So this is going to turn into sine squared over cosine squared. And this, being on the bottom, is the same as saying I'm multiplying by 1 over sine squared. Okay, keeping it on the bottom. And then our sine squareds will drop out. So we end up with 1 over cosine squared of x, and that is defined to be secant squared. All right, so this first day we're just using all of the different identities to try to simplify expressions, just getting ourselves familiar with those. All right, so your first assignment here, day 1, starts on page 410.